Hello everyone, this is Sharma and I welcome you all to my class. Okay, so as you already knew, the topic of discussion electricity and magnetic effects of electric current. So, first of all, let us know where did this concept of electricity actually originate? See, everyone would be in an opinion that this electricity is a concept of physics. But let me tell you, all branches of science are interlinked, they are related to each other. And this concept of electricity actually took its origin in chemistry. Remember, we came across the concept of charge, electrically charged particles, when we were discussing about the concept of atomic structure, where electrons are the charged particles which move from one place to another place or around the nucleus. Okay, now these charged particles, that means that is where when we are discussing about atomic structure in chemistry, that is when we actually came across the concept of charge. Okay, so we can say it took its origin in chemistry. Now, coming to the next part, the study of charged particles. Okay, how they behave, how they are going to behave is what we discuss in the concept of electricity. And this electricity is again classified into two types: static electricity and current electricity. Now, there is one more point which I wanted to say. If you have learned in periodic classification or metals and non-metals chapters anywhere before, you would be knowing that all elements which are having one, two, or three electrons in the outermost shell are called as metals, and all elements which are having five, six, or seven electrons, they all are coming under non-metals. Okay. Now these elements which are having one, two, or three electrons in the outermost shell, they are not very strongly bonded with the nucleus. So they tend to come out of the atom. So when they are coming out of the atom, they are movable. Okay, so they can move from one atom to another atom. Okay, that means there is a flow of charge or there is a movement of charge. Okay, so this is what is actually causing the charge to move from one place to another place. Now, how will the electron come out? What is the need for the electron to come out? This again goes back to Bohr's model of an atom. In Bohr's model of an atom, Niels Bohr actually stated that electrons will be moving from one orbit to other orbit, or one stationary shell to the other stationary shell, okay, by either absorbing or giving away the energy. Whenever we give some energy to an atom, electrons are the first to gain them. They increase their kinetic energy, they move faster, and that will bring it out of the atom. So these electrons, which can move from one atom to another atom, are called free electrons. So these free electrons are present only in metals. So why we are having electrons which can move? Yes, we have the reason now. We are now having the reason for the movement of electrons. Now coming to the next part. If these electrons are residing on the surface of one material, then that comes under static electricity. So, as I already said, electricity, the study of charged particles and their behavior, is classified into two types. One is static electricity, the other one is current electricity. So, if the charge is at rest on the surface of any object, then it comes under static electricity. For example, you might have noticed if you have dropped a few thermocol balls in a balloon and blow the balloon and shake them. When you burst the balloon, not all thermocol balls will be coming out. Only few, like most of the balls come out, but some thermocol balls they stick inside the balloon. Or actually, you can notice that when you blow air into the balloon and you hold it, you will see the thermocol balls are at the top. They don't drop down. They are devoid of the gravity. Now, why is that happening? It is because when there is a friction between the surface, the inner surface of the balloon and the thermocol ball, okay, that friction is producing heat as always. And because of that heat, these thermocol balls are losing their electrons and they are getting charged up. Okay, one element or one substance is losing electron, automatically the other substance will gain those electrons. When those electrons are gained, what happens? These two are oppositely charged particles, now substances, and they attract each other. And that is the reason why we are having a force of attraction between this thermocol ball and the balloon. Okay, now coming to free electrons. These free electrons tend to move from one place to another place. Okay, one atom to another atom, and it continues. Okay, so that is where we bring the term current. Current is a general English term which represents flow. Excuse me. If water is flowing from one place to another place, we say it is water current. Okay, in the same way, if electric charge is flowing from one place to another place, then we say it is electric current. So, this current. So, this is how we actually got the name to the chapter current electricity. Okay, now coming to the next part. Okay, we have to define current. Okay, how do we define current? We have to define current in terms of the charge that is flowing. Okay, so we define current as rate of flow of charge. Okay, so charge that is traveling, which is denoted by the letter Q. Okay, and whenever we use the word rate of, we divide by time. Okay, so rate of flow of charge will give us the current that is flowing through a conductor, which is denoted by the letter I. The SI unit of current is amperes. Okay, and it is denoted by the letter capital A. Ampere being the name of a scientist, it is always when you are writing it in full form, we write in small letters, and when we are representing in a symbolic form, we write capital alphabet. Okay, now this current, the speed with which the current is flowing, okay, the speed with which the charge is traveling, we call it as current. Now, why should the current flow? Okay, why should the charge travel from one place to another place? Okay, we all know that anything will be traveling from a place where it is more in quantity to a place where it is less in quantity. Okay, so let us see. If I hold a bucket of water, okay, which is at a higher level, maybe a meter high or 2 meters high, okay, and I place another bucket on the ground, I take a tube and I dip one end of the tube in the bucket which is at a higher level and the other end of the tube in the bucket which is kept on the ground. What will happen to the water? Obviously, this water would be traveling from the bucket which is placed at a height to the bucket which is at bottom, because the water is trying to travel from a place where which is having more potential energy. So potential energy is because of its position, from a higher position to a lower position. Okay, similarly, if there is a place, there is a point where there are more number of charged particles, say A, there is a point A where there are more number of charged particles, say 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Okay, and there is another point B where there is only one electron. Okay, so there are more number of charged particles here and there are less number of charged particles here, and I join these 2 points A and B by means of a conductor, conducting material. Now, what happens? Electrons are more in number here and less in number here. So they start traveling from point A to point B until they attain electrical equilibrium. So there are 9 electrons here and there is only 1 electron here. So they keep traveling until there are 5 electrons on each side. Okay, so that is how the charge traveling taking place, like the charge moves. Now there is one important thing I need to tell here. Here we are having more number of electrons, that is more number of negatively charged particles. So this is called low potential area. One will be doubting that as there are more number of charged particles here, it should be a high potential. No, it is not like that. We will treat positive charge as a measure of potential. Okay, and here absence of electron is treated as a positive charge, and there are less number of electrons here, which ultimately jumps to the like which for which we ultimately jump to the conclusion that there are more number of positively charged particles. Less number of electrons means more positive. So this will be considered as high potential area. Okay, so we have low potential area and high potential area. Now, even though it is the electron that is traveling from low potential area to high potential area, we say charge is traveling from high potential to low potential. Okay, so charge is traveling from high potential area to low potential area. Okay, now for this charge to travel, what should be there? There should be a difference in their electrical potentials. Okay, so that difference in the electrical potential is called potential difference in simple, and it is defined as the amount of work done in moving a unit charge from one point to another point. Now see, this is a point, and from this point, this charge is traveling. In this case, charge is traveling from B to A. Okay, now here for this charged particle to move, something should be acting on it. And what is that? Obviously, force. Okay, so there is a force acting on the charged particle, because of which there is a displacement. Okay, so force times displacement is actually giving us the work done. And on what is the work done? Work is done on the charged particle. Okay, so that work done per unit charge is called electrical potential, which is denoted by the letter V. Okay, and it is measured in volts. Okay, this also is the name of a scientist. Volta is the name of the scientist who actually invented the primary cell. Like he was working on the potential difference and cells, and it was named after him with respect. Okay, now we have voltage, which is defined as the amount of work done per unit charge. We have the definition of current, which is the rate at which the charge is flowing from one place to another place. Now coming to the relationship between current and voltage. There is one example which I always give in every class of mine. So if there are any students who came across me, would be knowing this example very well. If there is a glass tube which I am holding, which is 1 meter long, and there is one drop of mercury at one of its ends. Okay, I hold it horizontally, and as I said, it's 1 meter long, and I keep it at a height of 1 meter from the ground. How long would it take for the mercury drop to travel from one end to other end? Okay, good number of students actually gave answer to this question saying that the mercury drop will not move because I was holding it horizontally. Okay, as I was holding the tube horizontally, the mercury drop will not move. Now, suppose I tilt it slightly, then maybe this mercury drop will be taking approximately, say, a minute to reach the other end. If I tilt it more by a greater angle, then then the time taken by the mercury drop to reach the other end will be more. If I tilt it more, it travels much faster. Okay, that means what is happening when there is a difference in the potentials, that is the heights, when there is a big difference in heights, the speed with which the mercury drop is traveling is faster. Okay, it's more, the speed is more. Okay, so from this we can say if the difference in potentials is more, then the speed with which the charge or any particle travels will be more. The same thing is applicable here also. Okay, if V, that is the voltage or the potential difference, is more, it is directly proportional to the current. That means the current also will be more. Okay. Now, to get rid of this proportionality, I multiply with a constant, that is V is equal to I into R. Now, what is this R? Remember, in physics, we cannot take just any alphabet and say this is a constant I have taken. It should be a well-defined term. So this R also should be a well-defined term. Now, how do we define that? See, this R is actually called resistance. Okay, this R is called resistance, and this resistance is the ability of an object to oppose the free flow of electrons through it. Okay, some elements will be allowing, some substances will be allowing the charge to flow through them easily, and some substances don't find it easy for the charge to flow through them. Like, it is very difficult, they don't allow the charge to flow through them. Example, we can take wood is a poor conductor of electricity. Okay, and glass is total insulator, whereas iron is a very good conductor of electricity. Okay, only after gold, silver, platinum, gold, silver, and copper. Okay, so like that, what is happening? The ability to oppose the flow of charge is changing. Okay, it is good for some material, and good is average. It's okay for some material, and for some material it is very high. So like it's very low. So that ability of an atom to oppose the flow of charge, okay, is called resistance. Now this equation V is equal to IR is called equation for Ohm's law. Okay, so V is equal to IR is called the equation for Ohm's law. Now, uh, is there any condition for this Ohm's law? Is it applicable everywhere? No, it is not applicable everywhere. There are some conditions. Okay, so if at all you are asked with the definition of Ohm's law in any of your examination, you should first start with the condition. Okay, you should start with the statement. You should start with the statement under similar conditions of temperature at constant temperature and under similar conditions of physical quantities like area of cross section or length, then the rate of flow of charge is directly proportional to the potential difference across the conductor. Okay, so first one, temperature. Okay, temperature is actually affecting the speed with which the charge flows. How does it affect? Okay, see, when electrons are traveling from one atom to another atom, what happens? They are traveling, and remember, they are not like given way by the ions which are there in the path. This electron has to collide with each and every ion that is coming in its path. And when it is colliding, it is losing its kinetic energy, and that is changing into heat. Okay. Now, when the temperature increases, what will happen? That heat energy which is produced is absorbed by the ions, and they increase their kinetic energy, and they tend to vibrate more. Okay. Now, when they are vibrating more vigorously, automatically what happens? the number of collisions that are happening between electrons and these ions is increasing. Okay, if the ion is vibrating slowly, then electron might be undergoing some 5 or 6 collisions. Now if it is vibrating more vigorously, then the electron will be colliding with another 10 ions. So thereby what is happening, the speed with which the electron is traveling is decreasing. Okay, let me explain the same with help of a diagram. See, this is a conductor, let us assume. Okay, and these are the ions. Okay, now let us assume there is a one electron which is trying to travel through all these things and come out of this end of the conductor. Now, this electron, it comes inside, it collides with this ion, then gets deflected, collides here. So what is happening every time it is colliding? It is actually losing its energy. Yeah. So it has undergone good number of collisions. Now, what if these ions are vibrating? When they are vibrating, it is very clearly understood that more number of collisions will be happening. Here we considered ions which were at rest. They are not moving. Now, if there is an ion, okay, let us assume this ion, the electron came, collided with it, okay, and it went this direction. Now, by that time it bounces back and comes to the same ion, it would be in a different position, which makes it deflect in a different direction. So thereby what is happening, the number of collisions will actually increase. So from this we understand that if the temperature is increasing, number of collisions between the ions and the electron is increasing. Every time the number of collisions, like every time the electron is colliding with an ion, automatically it will be losing its kinetic energy. If it is losing its kinetic energy, that means it is not traveling faster, it is taking more time. And in the equation, I is equal to q by t, as I said, the time is increasing, the total value of I will be decreasing. Okay, the value of I decreases. Okay, so this is how the temperature is affecting. This is how the temperature is actually affecting the rate of flow of charge at current. Now, from this, what we can say, if the temperature is increasing, is the resistance not increasing? Of course, it is increasing. If the temperature is increasing, because the charge is not, the electron is not able to flow freely, the resistance is increasing. Okay, now area of cross section. So one thing we understood is the temperature. Okay, next, area of cross section. Remember, we can always compare the flow of electrons in a wire with the flow of water in a hose pipe. Okay, suppose I take a hose pipe which is having a broader diameter. Okay, and the water is flowing through it. It may not be gushing out, but yes, the surface of water which is in contact with the surface of pipe, it will be less, so less resistance, so more water will be flowing. Imagine there is a tap which gives me 1 liter of water in 1 second. To that I have connected a tube which is say 3 inches in diameter, 3 inches in diameter, and say it is 1 meter long. Undoubtedly, from the other end of the tube also, I will be getting 1 liter in 1 second, or maybe very little less, maybe some 10 ml or 20 ml less. Okay. Now, instead, if I connect a tube which is only 1 inch in diameter, will I be getting the entire 1 liter of water in 1 second? This is a question mark, because that may not happen, because more water is in contact with a more surface of the tube, and thereby the current flowing will be like the water that will be flowing per unit time will be less. Now suppose if I change the tube to an aquarium pipe, aquarium tube which is used so that we can connect to toys and that bubbles will be coming. Okay, so that air pump, air tube which is there in the aquarium. So if I connect that 1 meter long tube to a pipe which is giving me 1 liter of water in 1 second, now will I be getting 1 liter of water in 1 second from the other end of the tube as well? The answer is a very big no. Okay, see, from this what we understand, if the area of cross section is decreasing, okay, if the diameter of the wire or diameter of the tube or area of cross section is decreasing, it is not easy for anything to flow through it. Like it is not easy for anything to flow, whether it is water or electrons. Okay, so if area of cross section is decreasing, then the resistance is increasing. Okay, so we can say resistance is inversely proportional to area of cross section. Okay, now coming to the next part, that is length. See, length is that quantity which determines like the rate of flow of charge. Okay, again I insist on the word rate. That means this is only changing the speed, but nothing else. Okay, now yeah, as I was saying, again we compare this with the flow of water in a hose pipe. Okay, if I take a tap again which is giving me 1 liter of water in 1 second, I connect a hose pipe which is 100 meter long. Okay, and I open the tap. Now will I be getting the water with the same speed from the other end? Definitely not. It would be coming very slowly. Like, you don't get that speed. Okay, you can clearly identify that. Now, if I cut the hose to half, that means now it is only 50 meter in length. Now, what will happen? In this case, we notice that even though it is not 1 liter of water in 1 second, definitely it is more than earlier. Okay, we can clearly identify that the water will be traveling with a much faster rate. Now, if I cut that to 10 meters, okay, now the length is only 10 meters. Now we can see that most of the water is coming out. It may not be 1 liter in 1 second, but definitely like 900 ml in 1 second. Now, if I cut that to half meter, almost all the water will be like coming almost instantly. That means there is no change in the like there is no loss of speed in the flow of water. Okay, so like this, what is happening, if the length is decreasing, the speed with which the water is traveling is increasing. Or in other words, I can say length is direct, or resistance is directly proportional to length. Okay, now on combining these two, okay, I get R is proportional to L by A. Okay, R is proportional to L by A. That means resistance is directly proportional to length and inversely proportional to area of cross section. Again, this proportionality, it is only giving us a relation, but not an equation. To get rid of this proportionality, I multiply with a constant. R is equal to rho L by A. Now, what is rho? So that is where the last term comes. Okay. Nature of material. Okay. Rho refers to nature of material, and it is a constant. Okay. This is rho. This rho is called specific resistance or resistivity. Okay, so this rho, which is a Greek alphabet, is called specific resistance or resistivity. Okay, and it is dependent on the nature of the material, and it is unique. Okay, each material will have its own specific resistance. Okay, now from this, we actually understood what are the factors which affect the resistance. First one, the temperature, which we don't mention here anyway. Okay. Second one, area of cross section. If the area of cross section is more, then the resistance will be less. Length. If the length is more, then the resistance will be more. Nature of the material. Of course, it is unique and it is different for different elements. So these are the factors which affect the resistance offered by a material. Now coming to the next part. Do all material obey Ohm's law? Let us draw a graph between voltage and current according to Ohm's law. Okay. So we take I and V. Okay. Now if the current increases, if the voltage is increasing, the current also increases like this. Okay. Now, as long as we are getting a straight line, that means it is equal change in one quantity with respect to the other, with equal change in the other quantity. Now, will this always happen? As a matter of fact, no, it does not always happen. See, there are few materials which don't obey Ohm's law. For them, the graph goes like this. Okay, so for okay, if I take like this, okay, when the voltage increases, for equal change in voltage, there is an unequal change in the current. Okay, so these kind of material which do not obey Ohm's law are called non-ohmic conductors, whereas those which obey Ohm's law are called ohmic conductors. So ohmic conductors are those which obey Ohm's law, and non-ohmic conductors are those which do not obey Ohm's law. Okay. Now, if we have to connect, okay, now resistance, we know what is resistance. Here, let me introduce another word, resistor. I have seen students getting confused very often between resistance and resistor. Resistance is the property of the material, whereas a resistor is the component or it is the device which is offering resistance. Okay, now see, if I have to connect resistors like this kind of end-to-end connection of resistors is called series combination. Okay, now let us assume there are three resistors A, B, and C. These three resistors A, B, and C, these three are connected in series. Let us assume the resistance offered by A is R1, resistance offered by B is R2, resistance offered by C is R3. Okay. Now, when this is connected to a battery through an ammeter and a key, okay. Now, what happens to the this what will happen to the current and the voltage? Okay, see, this actually reminds me of one story wherein a king asks a question for which the minister would be asking for a block of ice. Okay, and he would be forwarding that block of ice to everyone in the what we call that court, and finally the last person will be getting a very small piece of ice or even water. That means what is happening when the ice block is traveling from one hand to other hand, from that person to another person, like that in everyone's hand in the court, it is actually getting distributed. It is making everyone's hand wet, and it is the quantity or the matter in it is actually getting distributed. The same thing happens here. Voltage actually gets distributed. Suppose this is V volts, the potential provided by the battery is V volts, then it gets distributed like this. Okay, in such a way that V is equal to V1 plus V2 plus V3. Now let us assume the current that is given by the battery is I. The current that is provided by the battery is I. Then what will be V1? Remember, the current should be flowing through the entire circuit through each and every resistor. Okay, that means current everywhere remains same. Okay, current actually remains same everywhere in the circuit because it is a series combination. So I will get V1 is equals to I into R1, V2 is equal to I into R2, V3 is equal to I into R3. So now this V is equal to IR as we know from Ohm's law. Now if I take I constant, I get IR is equal to I into R1 plus R2 plus R3. Okay, where I and I gets cancelled. So I get R is equal to R1 plus R2 plus R3. That means the equivalent resistance of three resistors connected in series is equal to the sum of individual resistances. Okay, this is a very important derivation as far as grade 10 students are concerned. Okay, now what if the combination is slightly changed? If we are having the resistors connected like this, okay, I name this as A, which offers a resistance of R1. This is B, which offers resistance R2. This is C, which offers resistance R3. And look at this, the way it is connected. These three are connected. Okay. Now you can see that all these three resistors are almost directly connected to the battery, so voltage will be same. If this is V volts, here also it is V volts, fine. Now the current that is coming, let us assume the current that is coming out of the battery is I amperes. After coming here, it actually gets separated. So let us assume the current flowing through this is I1. Now the remaining current after going here, it gets distributed, it gets separated, this splits up there to give I2, or rather this is I3 and this is I1. Now what happens? We are having three different currents flowing through three different resistors which are at the same potential. Now we have V is equal to IR. So I is equal to V by R. Okay. Now when I substitute, I know that the current that is coming from the battery is only getting distributed. That means I is equal to I1 plus I2 plus I3. So I1 is equal to V by R1. I2 is V by R2. I3 is V by R3. And now I take V as a common term. V into 1 by R1 plus 1 by R2 plus 1 by R3. That is V by R. Now V and V gets cancelled. I get 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. That means the reciprocal of the equivalent resistance of resistors connected parallel to each other is equal to sum of the reciprocals of individual resistances. So this is the equivalent resistance in case of parallel combination. So this is equivalent resistance in series and parallel combination. Now let us look into the next part where we come across the heating effects of electric current. Yes, definitely we all know that whenever electric current is passing through any conductor, it actually gets heated up. Heat energy is produced, and why that heat energy is produced, that already we have seen. Now Excuse me. Now, let us try to check what are the factors which affect the amount of heat produced. First one, current. Consider two devices. One is your mobile charger and the second one is your laptop charger and third one is your iron box. Okay. If all these three are switched on for the same amount of time, say 5 minutes, which one actually gets heated up more? Obviously, it is iron box. Why? Through your mobile charger, only 200 milliamperes of current would be flowing, whereas your laptop charger would be taking from 1 to 1.5 amperes, whereas your iron box, it takes more amount of current. That means if the amount of current flowing through the circuit is increasing, automatically the amount of heat produced also increases. So I can say H is directly proportional to I square, and this is because it is increasing exponentially. Okay. Now resistance. Okay. Yes, does resistance affect the amount of heat produced? Undoubtedly, yes. If the resistance is more, that means it is not allowing that electron or the free electron to travel. Okay, that means there are more number of collisions this electron should undergo before it could come out of the other end of the conductor. More number of collisions ultimately means that more amount of heat produced. So resistance is also affecting, and heat produced is directly proportional to resistance. Next one, time. This don't need any explanation. We know that if any appliance is switched on for a longer time, then the heat produced will be more. So we have H is proportional to T. I will take small t. Now combining these three, I get H is proportional to I square RT. Yeah, there is one more thing I need to tell you. There are two representations. One is capital I, the other one is small I. Don't get confused. Whenever we are talking about alternating current, okay, we use a small I. Whenever we are talking about direct current, we use capital I. What is direct current and what is alternate current? We will see in subsequent videos. So H is proportional to I square RT, and H is equals to a constant J into I square RT, where J is called Joule's constant. Anyway, for your syllabus as of now, this J does not come into play. It is H is equal to I square RT. Okay. So the amount of heat produced by the current carrying conductor is dependent on the current that is flowing, square of the current that is flowing to the conductor, resistance of the material, and time for which the current is flowing. Okay. Now, what is the main purpose of this electricity? This electricity is used in a versatile, like this is a versatile source of energy. Okay, electricity is a versatile source of energy. We can get many other things done with the help of electricity. Excuse me. Okay, so we can make a fan work, we can make a light glow, we can use this for making a electric oven work. Okay, different purposes. It's a versatile. Now, work is the word I have used, right? So let us calculate how we get the how much amount of work we are getting from this. Okay, let us take some basic equations into consideration. I will consider I is equal to Q by T. I will consider V is equal to W by Q, and I will consider V is equal to IR. These three equations I will take into consideration. Okay, first I have I is equal to Q by T. From this I can write Q is equal to I into T. Okay. Now I have V is equal to W by Q. From this I can write Q is equal to, or W is equals to V into Q, because I want to find the amount of work done. So W is equal to V into Q. Now substitute this Q here. I get W is equal to VIT. That means the amount of work done by any appliance is equal to the product of the voltage across the terminals of that, or the voltage that is supplied to the kind of appliance, into the time for which the current is flowing and the amount of current that is flowing. Okay, so W is equal to VIT. Now, we have another formula that, we have work done. What about power? Okay, we know that power is equal to work by time. So what I would do, I would send this T to the other side. I have W is equal to VIT. I will send this T to the other side. Here it is multiplying, so when it crosses equality, it becomes division. I get W by T is equal to V into I. W by T, work by time, rate at which the work is done, it is nothing but power. So I got P is equal to VI, or small I. Let me continue with small I in this case. Okay, P is equal to VI. Okay, now we have V is equal to IR, right? So if I substitute V is equal to IR here, so IR into I, that is I square R. So P is equals to I square R. Okay, so we see we are using only three equations. Okay, and we have obtained already one, two, three. Okay, three. We take this as three. We have got three derivations from three formulae from that. It is all interchanging. How well you mix up all these formulae to get the required quantity. Okay, excuse me, numerical questions based on this topic are very, very, very important for your 10th standard, whichever syllabus you are following. Okay, now with this, actually, the concept of electricity, current electricity, comes to a conclusion. Now, coming to the next part, that is magnetic effects of electric current. Okay, magnetic effects of electric current. Now, does electric current and magnetic field have any relation with each other? Okay, this all started with the experiment of a scientist named Oyster. Okay, Oyster stated, like, when he was doing an experiment with a current carrying conductor, which is like this. He took a current carrying conductor, he placed it along north south direction. Let me draw it properly. He took a current carrying conductor, he placed it along north south direction. Okay, okay, and now this is the current carrying conductor AB. Okay, here the current is flowing in this direction, and this is the place where he placed the magnetic needle. Now, what happens when it is switched on? The magnet started showing a different direction. It is showing like this, a different direction. Why is that difference coming? Whenever there is a change in the, like, whenever the current is flowing through a conductor and a magnetic needle is placed beside that, why is there a deflection? First of all, when does a magnetic needle show a deflection? Why will it show a deflection? See, magnetic needle shows a deflection only when it is placed in a magnetic field. We see a deflection in the magnetic needle only when it is kept beside a magnet, right? Suppose if I bring the needle anywhere in the room, no, it does not show any deflection. But if I bring it close to any magnet, it shows a deflection. That means a magnetic needle gets deflected by a magnetic field. Now, that magnetic needle is actually getting deflected and it is brought beside a current carrying conductor. Okay, so that clearly shows that around this current carrying conductor there is a magnetic field. There is a magnetic field around the current carrying conductor. Okay, because of which this needle is getting deflected. That is where the entire thing started. Now, that magnetic field which is existing should be having a proper direction. That is given by right hand thumb rule. Okay, so now we are knowing that there is magnetic field. Okay, there's a magnetic field around the current carrying conductor, so it comes under, this is studied under the heading magnetic effects of electric current. Okay, this is the magnetic effect of electric current. So right hand thumb rule. So if you take your right hand, fold all your fingers with your thumb rising up, then it actually shows you a representation. If this thumb is actually showing you the direction of the current, the direction in which these fingers are rolled will give you the direction of magnetic field around the current carrying conductor. Okay, so that is the right hand thumb rule. Now coming to the next part, where do we use this magnetic effects? Like where are we using these magnetic effects of electric current? Let us see. The first and foremost application is a DC motor. Okay, so DC motor, what does a DC motor do? It will be converting the electric energy into mechanical energy. Okay, so see, if I take two magnets, two magnetic poles, sorry. Okay, this being the north pole and this being the south pole. Okay, and I place a rectangular coil between these two. Excuse my excellent drawing skills. Yeah. Okay, I name this as A, B, C, D, and these are the two ends of the wire. Okay, so coil is nothing but a wire which is wound. Okay, now when it is connected to the battery, say like this. Okay, when it is connected to the battery like this, current is traveling from A to B, B to C, C to D, and back to the battery. Now there is one rule called Fleming's left hand rule. Fleming's left hand rule states that if the direction of electric current and direction of magnetic field are perpendicular to each other, the resultant would be perpendicular to both. The resultant force will be acting in a direction which is perpendicular to both. Always, index finger is the direction of magnetic field and middle finger is the direction of current. Okay, now you see in this case, this direction of magnetic field is in this direction and this is going like this. For your understanding, I have drawn it cross, but it is actually straight. Okay, so this is the direction of magnetic field and this is the direction of current. So what happens? The resultant force, that is the thumb, will be pointing into the plane of the board. Okay, so what it will be rotating. Okay, it rotates. This is the okay, this is the direction of magnetic field and this is the direction of current, so it will be turning in the same way here also. Or let me explain this with the help of my mobile watch. Okay, let us assume this is A, B. Okay, this is A, B, C, D. Okay, now this is the direction of magnetic field and this is the direction of current. So automatically in the direction of the thumb it should rotate, so this part will be rotating like this. Now the same current is traveling from C to D. So this is the direction of magnetic field. This is the direction of current. So this will be the direction in which the resultant force acts. So what is happening? This part is trying to move backwards. This part is trying to move forward. So we are having two forces which are equal in magnitude but opposite direction acting on the same body. And this is what we call a couple or a torque. So that will make this rotate. Okay, now when it is rotating, it should be rotating about an axis, so we place an axle here. Okay, so now we are having this coil which is rotating. Now after one rotation, what happens? These two wires actually get entangled and they break. Finished. The entire work done, entire hard work gone wasted. So what we should do to prevent that? There should be contact. At the same time, they should be free to move. For that, we have split rings. Okay. So split rings is actually, this pair of split ring is actually behaving like a commutator. What is a commutator? Commutator is that device which actually changes the direction of current. Remember, commutator is a device which changes the direction of current. Okay, so now when this A is coming this side, that means when it is rotated by 180 degrees, then this ring, split ring, say S1, is coming here to the place of S2, and S2 will come to the place of S1. There are two advantages with this split rings in this case. First advantage is, yes, the wires are not getting entangled and they are not breaking. Second advantage is the direction of current can be changed in the coil. Remember, the current is traveling from A to B, B to C, and C to D when it is in this position. When it has made a rotation by 180 degrees, then what happens? S2 is here. That means in place of A, we are having D. In place of B, we have C. Here we have B, and here we have A. And the current is now traveling from D to B, B to C, C to A. That means from A, B, C, D, like this it was traveling. Now the direction of the current has changed. From D, it is traveling to C, to B, and to A. Okay. So what happened? The direction of current can be changed. So the rotation will remain constant. Okay, it continuously rotates in the same direction. Okay, so this is the working of construction and working of a DC motor. Okay, do you know that our loco engines are actually made up are running on these DC motors, not AC motors? AC motors are actually no, DC motors are actually more powerful when compared to AC motors. Now, the second application is actually the converse of this. Always a scientist will be having thoughts, questions like, what will happen? What if this, if not that? Okay, these questions, why, what, when, are those questions which are bringing about a revolution in our field of science. See, if we are giving electrical energy, we are getting mechanical energy, right? That is happening in case of DC motor. If I give mechanical energy, do I get electrical energy back? Okay, that is the question that came in the mind of a scientist. So immediately he started working on a concept. Okay, and the consequence of that is AC generator. Okay, what is an AC generator? AC, alternating current generator. It is converting the mechanical energy that is provided by us into electrical energy. The arrangement of AC generator and DC motor are almost the same except for a very small change in the construction and a very big difference in the function. Okay, see, we have same two semicircular strong magnetic poles, north and south, okay, in which we are placing a rectangular coil, okay, say A, B, C, D, A, B, C, D. Okay, now this is working on Fleming's right hand rule, which says that if the direction of motion and direction of magnetic field are perpendicular to each other, then there will be an EMF induced in a direction which is perpendicular to both. So if I rotate this upwards, where the direction of magnetic field is like this, then the current will be traveling into the plane of the board. That means from A to B like this. On the other hand, when this is moving up, ultimately this will be moving downward. So this is the direction of magnetic field and this is the direction in which force is acting. So I see this finger, the middle finger, which represents current, pointing out of the plane of the board. So the current is traveling from C to D. Now what is happening? We are having current traveling from A to B, B to C, C to D. Now, after a rotation of 180 degrees, which I will represent like this, okay? Now, after a 180 degrees rotation, okay, what happens? The current will start traveling in the opposite direction. Here we will be having B and here we will be having A. Now, this A to B is going like, current is traveling from B to A instead of A to B. So I can represent that with continuation of the wave like this. So we are having a positive cycle for half of the rotation. For the remaining half of the rotation, we are having negative cycle. So altogether, we are having a positive and negative coming one after the other. Okay, alternatively. And that's the reason why it is given with the name alternating current. Positive and negative come one after the other alternatively. So it is called alternating current. Okay. So now, the difference in the construction I was mentioning, instead of having split rings, this actually has slip rings, okay, through which this axial passes, and this is connected by means of carbon brushes, okay, and it is not the battery it will be connected to any substance which actually consumes that electrical energy produced, okay. So this is about AC generator and the magnetic effects of electric current. If there are any other questions which you want to ask me about this topic, you can always find me over WhatsApp on 9848302938. Okay, I hope this session was useful and helpful. Until we meet next time, have a nice time. Bye bye.